Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is the part 6 in a little mini series that I'm calling Repeated Measures One-Way Fixed Effects ANOVA. And we're going to look at contrast within this model. Now, as a reminder, the general model is y is equal to x beta star plus epsilon. And then we partition this into an overall mean, treatment effect, and between subject effect plus error. And look, watch parts 1 through 5 for much more detail on each of those. This is just a reminder. The beta and epsilons are normally distributed with constant variances. The betas and epsilons are independent. Now, contrast for the beta parameters, so that's these right here. So these are the subjects. Now we randomly pick subjects, and so creating linear, or contrast for the beta parameters really don't make sense. The beta parameters are random variables. They're not constant, fixed unknown parameters where we want to estimate them. These are just observations of random variables. So it really doesn't make sense. So we're only interested in treatment contrast. So linear combinations of these taus. So gamma is a contrast in the taus if gamma can be represented like this, where it's the sum of the CI times tau I, and there's A from 1 to A, but the CIs have to add to 0. Then it's a contrast in the treatments. Now, I have a 4-part little mini series on estimability where we went in great depth about estimability. But this gamma in a larger picture has to be a linear combinations of the betas. So this beta parameter. Now, granted, we're only interested in the taus. So this lambda vector is going to have a 0 in the first component. That way when we do this multiplication, that mu parameter is not picked up. And then all these are 0, so the betas aren't picked up. And then the C1 through CA is the linear combination of the taus. And these have to add to 0 to be a contrast. So that means lambda prime 1. So that means the sum of all these has to be 0. And to be estimable. Now, what does estimable mean? Estimable means that there is a unique value for this linear combinations. Now, to me, it's actually so surprising how it all works out, because we create a least squares estimate for beta, which is not unique. But then somehow taking a linear combination of these beta parameters, we can find a unique value. To me, I love the theory behind that, but I'm going to point you back to my little mini series on estimability. So for this to be estimable, then this lambda parameter has to be part of the row space of the design matrix X. And this is in row, of course, is in NA space, right? It has, because this matrix is NA by 1 plus A plus N, right? Because we partitioned it into these sections. So we have a theorem here. So let's let lambda transpose beta star be estimable, and that let rho prime x be this lambda. Okay. Then lambda beta star is a contrast in the taus if and only if rho prime m is equal to rho prime m tau. Now remember, m is the perpendicular projection matrix on the whole column space of x, which, x is the augmented matrix of 1, x tau, and x beta. This has to equal rho prime m tau, and m tau is the perpendicular projection matrix on the column space of x tau. Now this implies that the least squares estimate for this, remember that this piece here is the least squares estimate for beta tilde, and it's not unique, right? That's a generalized inverse. And then lambda is part of the row space, right? But then this piece here is m, And we're saying that it has to equal m tau, so that's this. But this right here generates the treatment mean vector, and then this is a linear combination of the treatment means. And so this is going to create this linear combination of the treatment mean, CI times each treatment mean. And this is exactly what we did in one-way fixed effects ANOVA. Okay, so note that M is the perpendicular projection matrix on the column space of X, which is the augmented matrix 1 x tau x beta, and m tau is the perpendicular projection matrix on the column space of tau. See parts 1 and 2 for much more detail. So let's prove this. So note that the column space of m tau minus j is a subset of M. Remember, M is x tau plus x beta minus j. So if we only take a part of that column space, it has to be a subset of that full column space. So this is true. But both M and m tau minus j are perpendicular projection matrices. So then, by property 7 in the video I have called perpendicular projection matrices, M minus m tau minus j is a perpendicular projection matrix. So rho prime, so remember this is the linear combination of the betas that we're interested in, is part of the rho space, but X is this augmented matrix here. And so rho times this is that, rho times that, rho times this. But remember, we want this first piece to be 0 because we don't want that mu parameter, and we want these to all be 0 because we don't want any of the betas. And this is actually the C1 through CA, right? Because that's the linear combination of the tau parameters that we're interested in. Now, granted, these have to sum to 0. Now, this implies that rho 1 is 0 and rho x beta is 0, right? Which means that rho is orthogonal to this 1 vector, and it's actually orthogonal to x beta, right? Has to be, because it's 0. Now, 1 beta is actually the same column space as x beta, right? Because if you add all these columns, you get 1, right? So this is a dependent vector. So we can leave it out, and the column space spanned by this is the same. But this is the same span as if we put the perpendicular projection matrix of this x beta, which is m beta. Now this we can rewrite like this, right? Because we have m tau minus m tau, plus j minus j, and m. So we've added a well-chosen 0 here. But this is m, and this is m tau minus j. But we said this was a perpendicular projection matrix. So thus, since rho is orthogonal to this column space, which is the same as this column space, this has to be 0. But when we multiply this in, which implies we get m rho m, and then multiply that in and take it over, is equal to rho m tau minus j. But then we can take this into both of those, and we said this was 0, right? J is a perpendicular projection matrix on the column space of 1, but we said rho 1 was 0. So this drops out, and we're only left with rho m tau. But that's what we wanted to show, that rho m is equal to rho prime m tau. Okay, so to me, it's huge. It makes making contrast in this repeated measures design so much easier. We only have to think about linear combinations of the treatment effects, or the taus, in order for it to be estimable, right? That's a huge part, okay? So note from the series in one-way fixed effects ANOVA. So this is another mini series that I did in the playlist General Linear Models Design of Experiments. We showed that m rho, now remember this m is the m in this matrix, or in this video. it is rho star, which had this form, C1 over N all the way to, N of those, and then CA over N to C over N, N of those, and then, this one would be C2 over N, N times, etc. And this is for all rho that satisfies this, the rho prime M X is lambda. Satisfying this. So the least squares estimate, remember in this video, is this. So it's gamma, which is lambda per beta. And now remember, this beta only had the mu and then the tau 1, tau through tau A, right? So then the least squares estimate is this. And then M times Y, this is M, but then this created the treatment mean, and then this created the sum of the CI-YIs. Okay, so this is the big note. Okay, so this was a reminder. Now the M in this vector, so this is M, but this X actually is equal to X tau in this video that we're doing here, right? And we said rho M has to be rho X tau, and this is the column space of X tau. So this is equal to M tau in this repeated measures one-way fixed effects ANOVA. And so we construct contrast and orthogonal contrast exactly similar to the way we did in one-way fixed effects ANOVA modeling. And this includes partitioning the sum of squares treatment. And that just makes it so much easier to think about when we're in this design. Now I think that this may become more clear when we do the example in R software, which is the next video. So that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.